Good evening, everyone. Today we will continue with our previous discussion about the phase portraits of metric differential equations. In the previous video we covered the first cases of eigenvalues, of real eigenvalues that were different. So now let's continue with the case of equal eigenvalues. Let's say we have the same eigenvalue with multiplicity, with algebraic multiplicity 2. And then we know that a first case could be that both are negative or less than zero. So the flux of this matrix, which were the Jacobian matrix, right? So this flux was equal to the same eigenvalue, well, this term times the x, which we write like this, and then this is equal to these terms. So now, what happens when both are negative? Well, since we can draw the Cartesian plane, so if we take some initial value here in this axis, let's say x1 is equal to some positive value and x2 is equal to 0, and then this flux, when t grows, you know that since lambda is a negative number, then this will tend to 0. So in this case the flux goes like this, and the second coordinate doesn't move because this constant is equal to 0, then it just stays in 0 in this axis. So for when t goes into minus infinity, then this term becomes increases this term, and the exponential of an increasing term goes to infinity. Then we draw it like this. Similarly, we can show that for the other branch of this axis, the flux goes like this, and you know that the origin always is same there at the origin, and for a point here in the other axis, the situation will be similar because the eigenvalues were equal. And now the relevant case could be what happens when we take a point here, when both are positive numbers. When t goes into infinity, the same argument shows that this goes straight into the origin. Now this could be a line with 45 degrees. It could be in this case because we can take these two constants equal, so it is possible. If they are different, like if we are here, then it will go with some slope like this, and similarly the other part will be like this. So in this case the origin is an attractor like before, for the same arguments also, because you know that we say that the origin is an attractor whenever the real parts of the eigenvalues were negative. So in this case the eigenvalue is only 1, so we were saying that the eigenvalue was a real number and that it was negative, so the condition is fulfilled and the origin is an attractor. The only difference with the previous case was that was the shape of these fluxes, right? Because in the previous case they had some slope that was changing. We could say that the derivative was changing, was increasing or decreasing. but in this case they are lines, they are straight lines, so the derivative is constant. So the next case is quite straightforward also. What happens when both eigenvalues are positive? So the situation will be reversed, right? It's not difficult to see that. So the origin always stays at the origin, and then the fluxes will go away from the origin and in lines away from it. It's just the same analysis that we have been doing since the previous video. So this is clear, and so the origin is a repeller because the real part of the eigenvalues is positive. So this is a characterization. The last case would be what happens when both eigenvalues are equal to 0. So in this case it is interesting because now the flux of this Jacobian matrix will be, if the eigenvalue is 0, then this is 0, the exponential of 0 is 1, so this will be just this column, right? So for every point that we take besides the origin, everything just stays there. So nothing moves. The flux is always constant. So we say that for every point in R2 in this case, the orbit of x is equal to x. So the orbit is is the trace of the flux with a fixed. Let me write it. It's a trace of the flux of a fixed initial value. The thing that we are doing here, right? So if you fix this thing, then this becomes a function of time, of t, and then the image of the function is the orbit. So the orbits are just points, and this happens whenever x is an element of the kernel of the matrix that we are studying. So here it is equivalent to say that the kernel of this matrix is the whole plane. So this makes a lot of sense because you know that if the eigenvalues were equal to 0, then the matrix was actually the 0 matrix. So it makes complete sense. Now we just need to discuss the last case. So in the previous video we covered everything about different eigenvalues, different real eigenvalues. Now we have done the part of equal eigenvalues, and the only thing that is left to do is to work complex eigenvalues. You know that the characteristic polynomial of our matrix, of our Jacobian matrix, or matrix that is in its Jacobian canonical form, it is a function, well, it's a polynomial, of course, of second degree. Let's say a constant a0 lambda square plus a1 lambda plus a2. So this is a polynomial with real coefficients. Everything here is real. And then when you find the roots of this polynomial, then the roots, if they are complex, then they will be always conjugate roots, meaning that the first root will be, let's say, will be equal to the conjugate of the second root. So they come in pairs, right? So let's say that our root is, the first root is this thing, and the second root is this thing. So you know that b is different from 0 because otherwise it would be a real number. And now we want to calculate the exponential of this matrix And you know by theory that this is equal to the exponential of at times the cosine of tv. Here the same. This is a property minus the sine of tv. So this is a known fact. So the flux will be equal to this thing times the vector. Now, what happens when you compute this product? Well, let's calculate it. This is the cosine of tv plus x2 sine of tv, and below is minus the sine of tv plus x2 the cosine of tv. This is a row, and well, it is multiplied by this scalar. Well, it is a function of time also. Let's write it off just to make everything clear. Let's write it like this. So this is our flux. And now, once again, we need to study case by case. And so first, you know that v is different from 0, so we are freed from that case. Then v could be positive, it could be negative, a could be positive, could be negative, and we have all of those combinations. But it is not really, perhaps not necessary to study positive and negative imaginary parts, because you know that if the first one is positive, then its conjugate will be negative and so on. So it's just doesn't provide that much information. So we will be sticking with a positive imaginary part. And then what we really need to study is what happens when a is positive or when a is negative. A could be also be 0. So we have three relevant cases. So let's study them one by one. The first case will be a is positive and b is of course also positive. So what happens here? Let me copy this real quick. So this is a flux, and now a is positive, so this is the exponential of a positive constant times t, and well, b is positive, so let's highlight this. This is the first case. So let's try to analyze what's going on here. So let's say we fix some point. Well, the origin always stay at the origin, that's a given, always. And now what happens when we take a point here? A point in this axis with a positive, so a point with a positive first coordinate and 0 second coordinate. So here x1 is positive and x2 is equal to 0, so this thing cancels out. It just doesn't matter. And now we have a cosine of tv, and below we have minus sine of tv. You know that the cosine and sine are periodic functions, so they will have some bounded variation. It won't change really that much. But the thing that is really interesting is that this term here, when t goes into plus infinity, will go into plus infinity. So even though this part has a bounded variation, the whole thing will blow up. So let's see what happens. So this is interesting because it's at first sight is kind of difficult to analyze, but when you make this thing a little simpler, it becomes clear. So suppose for a moment that this part is constant, that everything here is constant. What happens when t changes, when t increases? Then you know that if you have a function that is cosine of t times some constant and minus sine of t with that constant, you know that this describes a circle that, let's say, we draw this around like this, and so this is in fact a circle. The only thing that we need to take care of is whether the circle is going like this or in the other direction. So quickly we can see that what happens. Let's say that here t is equal to 0 because it's the initial point. And what happens when t increases? Well, you know that the cosine of something starts at 1, and then when the angle increases, then the cosine decreases. So this thing will shrink into the origin, and that's obvious whatever direction you go. But the sign, the minus sign, when t increases, sign starts in 0, but then it grows, so it goes positive. So we have here minus sign. Then when t starts to grow, when the angle increases because b is also positive, then the sign will decrease. So it should be like this. So now we multiply this by this term that is increasing. Then this not only increases in this with constant radius, but this thing will start to get away from the origin. So the flux here goes like this. Let me draw it like this. So it is very interesting. And what happens when t goes into minus infinity? Then this radius decreases, so it will go like this. Wait a minute. Like this, going into the origin but never reaching the origin. So from here, well, you could try to analyze the more complex case in which when you take an initial point, let's say, what happens when you take a point here. So this is the initial point, then this is different from 0, this is different from 0, and then you will need to calculate those orbits, but it doesn't really, it's not that important to do it. And you could, of course you could do it, and it is perhaps more simpler to understand when you remember in linear algebra that this matrix describes a rotation. This is a rotation. So it is of course going to be something like this, even though it will be kind of more complicated when you take another point that doesn't have some coordinate equal to 0. It's just the same, because this matrix is in fact a linear transformation that is a rotation. So it will be like that. Then the other case, the second case, would be what happens when a is negative and b is positive. So just the same argument. Take a point here and see what happens. Is the when you fixed this term here, when this is fixed for a moment, just to analyze it more easily, when you fix that point, then this thing goes like this, and when you plug this function into play, then when t grows, the exponential decreases because a is a negative constant. So this thing will go straight into the origin. And let me use orange like this. So it will go straight into the origin, and similarly it will go when t decreases, it will be like this. So this is the flux. Now let me put And of course, the last case is kind of more easy because we were saying that all along. In the last case, when A is equal to 0, then the orbits are just circles. Like this. Oh wait. Circles like this. So all of the orbits are circles. And of course the origin is always at the origin, it never moves. So everything will be circles. And in this case, it is also kind of interesting to point out that the foliation, i.e. the collection of all of the orbits, such that x is a point here, well, in this case it is R2. The foliation is a partition of, this is a partition of R2, and with this Jacobian matrix, with these fluxes, what we are doing is to partition the whole plane into circles. So it is kind of interesting. If you ever need some way to partition the whole plane into circles, then this thing will be the way to go. This flux, the flux of a matrix with complex eigenvalues will be the way to go. And very quickly we can discuss what happens when B is negative, given the same case when A is positive. If you take a point here, let's say at the same point, when you take the same point, what will happen? Well, since B is negative, when you graph the trigonometric circle, so when t increases, since t is multiplied by a negative number, then the angle in fact decreases. So it will be a negative angle. And the cosine always decreases, but the important point is what happens with the sine. So the sine here will decrease, will be negative. But we were under this hypothesis, so we had a minus sign. So it won't be negative, but positive. So here, instead of going downwards, it will go upwards. So it's kind of, let me write it here. So when A is positive and B is negative, it would be, let's draw a circle to, yeah, and it will go like this. Lines getting away and then going into the origin. So it's kind of the opposite of the previous case. That's why I said in the beginning that we really didn't need to analyze that case, because it's the same. And they are in fact isomorphic, this foliation, and the other one is isomorphic. You can, let's put it one besides the other. You can see that pretty easily. You could perhaps define some function that connects each orbit with, that connects each orbit with the other one. Let's say that you take the points in this, because you know every orbit crosses this axis, the positive part of the axis, at least one time. So you could perhaps link each orbit here. Let's say the orbit that crosses the orbit that crosses this positive part of the x1 axis when t is equal to 0. At this point could be carried by a bijection probably to the other orbit when B is positive. that crosses the positive part of the x1 axis when t is 0 at that exact same point. So this is a bijection because it only crosses that point at time 0 one time, and also in the other case. So you could define that bijection. And this is everything. If you have any questions, you can write it down in the comments. Also, if you like that video, please give a thumbs up and subscribe to my channel. It will help me to grow the channel. And if you're interested in another topic, you can write it down in the comments below and I will try to work on that. So see you later.